highlighted global unpreparedness for the impact of large-scale global events. The tsunami from the Hunga Tonga Volcano in Tonga on 15 January 2022 was the first in a series of catastrophic eruptions for over 130 years, the last being the eruption of the Krakatoa volcano in Indonesia in 1883. Hunga Tonga. It was also the first multiple eruption tsunami since the Krakatoa event, and the first recorded by modern technology. The resulting shock wave was the most significant ever recorded, and the volcanic eruption was the highest on record. The Hunga Tonga event is comparable to the Papua New Guinea undersill landslide tsunami in 1998, which resulted in 2,200 deaths, and the 2004 India earthquake tsunami, which killed more than 250,000 people. All of the mechanisms are different. They all identify a previously unknown tsunami hazard. Papua New Guinea's underwater landslide generated a highly destructive tsunami, while an incident in the Indian Ocean saw a tsunami of high-magnitude earthquakes strike along a convergent boundary beyond the Pacific Ocean. Volcanic activity along Tonga's convergent boundaries is not unexpected. Hunga Tonga last erupted in 2015, but the magnitude and violence of the 2022 eruption is truly astounding. The unpredictable nature of eruptions reveals that the global hazard of large volume volcanic eruptions is underestimated and identifies global unpreparedness for the impacts of these events. Globally, there are 42 volcanoes that have the potential to erupt on a scale similar to Krakatoa and Hunga Tonga. So the events of 15 January 2022 should serve as a warning of the potential dangers of another cataclysmic eruption. Many of these volcanoes, unlike Hunga Tonga are close to high-density coastal populations. So far, there has been little publication on the mechanics of local eruptions or tsunamis. More than 100 papers on the event have been published, but most focus on satellite data recordings of atmospheric disturbances due to shock waves and far-field tsunamis. Both are caused by changes in atmospheric pressure at sea level, which initially give rise to small waves that increase through a process called resonance, which is determined by the relationship between the speed of the shock wave and the speed of the tsunami. There are still fewer papers on local or imminent tsunamis. This mechanism is still uncertain. There are several possible causes of this tsunami, including pyroclastic density current collapse, caldera collapse, and phreatomagmatic explosions, where magma interacts with seawater. One of the fears of the eruption was the impact on the climate, possibly from sulfur dioxide, SO2, but measurements indicated that the volume of SO2 was quite low. Even more surprising is the volume of water pumped into the atmosphere. Recent studies show this to be a high volume that can affect the climate. As for warnings about the effects of the event, there has been little backlash so far. This can be attributed to the volume of unpublished papers, such as seafloor mapping in the region. This unpublished paper could add to the uncertainty over the local tsunami mechanism. The source of the catastrophic peak explosion has also not been determined, whether it was the mixing of magma beneath the caldera or the ingress of cold water in the building during the final phase.